Hello and welcome to this presentation of our submission to the IBM Watson Analytics Global Competition 2017. My name is Ron Patain and I'm presenting on behalf of my team from the University of South Carolina Upstate. This project explores the relationship among four variables as measured in the urban areas of Beijing, China between 2013 and 2016. These variables include the average daily air pollution levels from a measurement of heavy fine particulate matter of size 2.5 micrometers. This variable is annotated throughout this presentation as PM 2.5. The second variable is the average daily temperature in this area over this time period. The third variable is the number of hospital emergency room visits for total and cause-specific respiratory disease. The fourth variable is the number of Twitter posts that include the hashtags Beijing and smog. Our fundamental question is, does there exist a relationship between these four variables? First, we need to gather the data. Air pollution and temperature data were sourced from the World Bank and from the U.S. Department of State Air Quality Monitoring Program called Mission China. Daily counts of respiratory emergency room visits were obtained from 10 general hospitals located in the urban areas of Beijing, as reported by Xu and colleagues in April 2016. Twitter data was obtained through IBM Watson's Social Analytics module. Let's begin by looking at the air pollution data. This map shows the average air pollution levels in countries around the globe in 2015. The darker the color blue, the higher the concentration of atmospheric air pollutants. While not a country with the highest air pollution, China nonetheless ranks toward the higher end of the scale. This bubble graph shows that most daily PM 2.5 values in Beijing are categorized in the unhealthy, very unhealthy, and hazardous categories of the Air Quality Index. This dashboard displays various analyses of the PM 2.5 data. The graph on the top left displays PM 2.5 levels by hour. Listed along the x-axis are the 24 hours in a day, and the y-axis shows PM 2.5 levels. This plot line shows higher concentration levels of PM 2.5 during the nighttime hours when temperature is lower. The graph on the top right displays average PM 2.5 levels by month. The months January through December are listed along the x-axis, and the vertical bars represents PM 2.5 levels. The taller the bar, the higher the concentration level of PM 2.5 in the atmosphere. This graph shows higher concentration levels of PM 2.5 in the colder winter months. The graph on the bottom left plots average air pollution levels in Beijing from 2013 to 2016. PM 2.5 levels decreased annually during this time. For this 4-year measurement period, air particulate matter of size 2.5 micrometers decreased almost 25%. The word cloud on the bottom right shows the most common values of PM 2.5 concentration levels by hour. Most of these values fall into the unhealthy or very unhealthy categories of the Air Quality Index. A decision rules analysis shows that carbon monoxide can predict PM 2.5 levels with a strength of 54%. Next, let's combine air pollution and temperature data. In this graph, we see an inverse relationship between these two variables. The blue bars indicate the average monthly temperature in degrees Celsius, and the green line indicates the average monthly PM 2.5 levels. Looking at both ends of the graph, as temperatures decrease in the winter months, the PM 2.5 levels increase. Looking at the emergency room data, we see an increase in the number of emergency room visits in 2013 for upper and lower respiratory tract infections represented by the blue and green lines respectively. Combining PM 2.5 levels with reported emergency room visits, we find that when the value of PM 2.5 is higher, there is a corresponding increase in respiratory-related emergency room visits. Thus far, we've discussed 3 variables. Let's now show them side by side. This dashboard displays 3 graphs. Each graph plots the variable over 12 months. The graph on the top left plots the average level of several air pollutants over a year. Notice the general U-shape of the blue, red, and green lines during the 12-month period. The graph on the right plots the average number of respiratory-related emergency room visits in a year. Again, notice the general U-shape of the lines. The graph on the bottom right plots the average temperature over a year. Here, the data graphs as an inverted U. If we were to overlay these 3 graphs, the top 2 graphs would show higher values near the endpoints and lower values in the middle, whereas the bottom graph is the opposite, lower values near the endpoints and higher values in the middle. Overlaying these 3 graphs of air pollution, emergency room visits, and temperature would look messy and be hard to read. Let's use a different graphic to combine the data for these three variables. This graphic combines our three variables, air pollution, temperature, and emergency room visits. The x-axis combines temperature into four groups. The colder temperatures are on the left, and temperatures increase in warmth as it moves to the right. The y-axis combines PM 2.5 values into 6 groups corresponding to the air quality index. The highest concentration levels are at the bottom of the axis. These correspond to the most hazardous levels of air pollution. Moving up the axis, air pollution concentration levels decrease. The blue-colored boxes indicate the number of respiratory-related issues. The darker the color, the higher the number of emergency room visits. Looking at the darkest color blue in the lower left corner, we see the highest number of emergency room visits occur when temperature is lowest and the air quality is most hazardous. Let's take a quick look at the Twitter data. Here's an analysis of Twitter posts over time. The y-axis counts the number of tweets containing the hashtags Beijing and smog. This graph shows a marked increase in the number of tweets about smog during the colder winter months. These graphs break down a count of 961 tweets by month about Beijing smog, collected from August 2015 to June 2016. The top graph shows a large number of tweets about Beijing smog posted in December. The bottom graph shows an analysis of the tweets' contents. In November and December, many of the tweets about Beijing smog convey a negative emotion. In conclusion, the analyses produced by Watson demonstrated a strong correlation between our three variables, air pollution, temperature, and emergency room visits. When temperatures are low, air pollution is high. This is correlated to a rise in emergency room visits for respiratory-related infections. The Twitter analyses reveal that there is still much work to be done to clean up the air in Beijing. We hope you have enjoyed this presentation. Thank you for your time and consideration.